We may be interested in examining whether two quantitative variables seem to have a correlation or relationship. For example, exam scores may be positively correlated with the time spent studying. So we may expect exam scores to increase as the time studying increases. Also, fuel efficiency in miles per gallon may be negatively correlated with the weight of a vehicle. We would expect fuel efficiency to decrease as the weight of a vehicle increases. So those are two basic examples of two variables that are correlated or potentially correlated together. So we may also examine relationships between a variable and time, where both variables are quantitative. Remember, quantitative means that they're measured with numbers. So the CDC, okay, that's the Center for Disease Control, data below gives the approximate number of deaths in thousands due to drug overdoses in the U.S. So in 2002, there were 23,000 overdose deaths. In 2005, there were 30,200 overdose deaths, and so on. Okay, so what we're going to do is we're going to create a scatter plot. So we're given a set of numerical data of the form XY. We can create a scatter plot. X is called the explanatory variable, and Y is called the response variable. So identify the explanatory and response variables in this situation. Well, X will be the number of years since 2002, and the Y value will be the number of deaths. Okay, so the response variable is the number of deaths in thousands. Now, one of the reasons that I defined the explanatory variable to be the year since 2002, I go ahead and actually define it for you right here in the next part. But it's very common to define an X variable when it's years. It's very common to define that as the year since a certain year. What that allows you to do is put in much smaller numbers for the X values. So when we say that X is the number of years since 2002, that allows us to use X equals 0 representing the year 2002. So one of our goals will be to write an equation relating X and Y together, or the explanatory and response variables, relate them together with an equation. So it's going to be easier to substitute a number 0 in rather than the year 2002. Okay, so to see a scatter plot on our calculator, we can follow these directions right here. And you can read those, but I'll just go through them on the calculator. Okay, so what we want to do is press second Y equals. Okay, it says stat plot. We want to make sure that plot 1 is on. So I'm going to press enter to go into that menu. Make sure the on is highlighted in black. And then the very first type of graph, that's a scatter plot. So it looks like a bunch of dots. And you also have box and whisker plots and your histogram. So going to that menu is no different than what you should have done before. Your X list is list 1. That's your X values, your years since 2002. And the Y list will be the Y values for your explanatory variable, the number of deaths in 1,000. So if I now go to my stat and enter them in the list, and you should have done this before, you could enter the number of years since 2002 in list 1, and then list 2 is your number of deaths in thousands. Okay, so pause the video if you need to, but I'm going to go on. Now if you do zoom stat, which is option 9, it'll give you the scatter plot. Okay, a scatter plot is just a fancy way of saying the points. So the reason we do that is we want to be able to answer, is there a general trend or pattern for the number of deaths? Well, we can see here that as time goes on. So as you go to the right, the Y values, or the number of deaths, increases. So the general trend, yes, there is a general trend. As time increases, or as time goes on, the number of deaths increases. Okay, the next thing we look at is the strength of correlation. Now we can see here that it looks like on ours, it looks like the points are very close to a line. Okay, so if we can imagine a line being drawn here, it looks like those points are very close to the line. So there should be a fairly strong correlation between time and the number of deaths. Now in general, you have several different types of correlation. Okay, meaning you have positive correlation or negative correlation, and then you have perfect high or low in each of those realms. Okay, so the values beneath the scatter plots show the value of R, which is called the linear correlation coefficient. Note that R is a value between -1 and 1. The closer R gets to 0, the less linear correlation there is between the variables. A perfect linear correlation is an R value of -1 or +1, which means the model will pass through every point on the scatter plot. Okay, so the R values are these numbers below each of the graphs. A perfect positive correlation. Positive because the points seem to be increasing, so going up. Perfect because if you were to draw a line, that line would pass through every single point. So that data set would have an R value of 1. A high positive correlation, again positive because you can see a general upward trend. A high positive correlation because if you were to imagine a line drawn that was increasing, that line would be fairly close to the points. So that's a high positive correlation. A low positive correlation, the R value is about 0.3, but you can still see a general trend upward. But if you were to draw a line going in the upward direction, those points are more scattered around that line than they were for the high positive correlation. Okay, negative correlations are the same idea as the positive correlations, except you have a decreasing trend or a downward trend rather than an upward trend. No correlation is when you look at the points just scattered all around the graph and you can't get a linear pattern out of that. Okay, whether you draw the line here or this way or straight across, okay, there's no line that is closer to the points than any other line. Okay, so that will be an R value of 0. Okay, so how do we actually find the R value for our example? Well, we know that based on what the scatter plot looks like it's a pretty high positive correlation. So the way we're going to do that, we're going to turn our diagnostics on by pressing second 0. You see how above the 0, there's a catalog. So we'll have to do this one time, second 0, and that'll take us to a catalog, and we need to scroll down to diagnostics. Okay, so scroll down to diagnostics on, press enter, and then enter again, and they'll be on. I'm not going to go into detail what that means. You just need to do it first. Now, some of yours already may be on, but just do it just to make sure. Okay, so now, once our diagnostics are on, we're going to go to stat, calculate linreg, a plus bx, and then we're going to do it on list 1 and list 2, or x and y. Okay, so stat, calculate. Now you notice there's an ax plus b. You can use that one if you want. The only difference is a is the coefficient in the linreg ax plus b. A is the coefficient of x. and in the a plus bx, b is the coefficient. There's a reason why two of them are on here. I'm not exactly sure or don't remember what it is. But I'm just going to use linreg a plus bx. Whichever one you use, just make sure you put the a in the correct place and the b in the correct place when you actually get to the step where you need to write your equation. Okay, so linreg a plus bx, and then second 1 for list 1, comma, second 2 for list 2. Okay, and then you'll actually have the y equals a plus bx pop up here, and you'll have your a and b values, and this is just going to be the equation for your line, which we'll get to at a later point. Okay, right now we're focused on looking at the R value, so how correlated are the time and the number of deaths due to overdoses? Well, the R value is 0.9962, if you round it. Okay, so 0.9962, what does that tell us about the number of deaths and the year? So what's the correlation between them? Well, 0.9962 is very close to +1. So we'd have a very high or very strong positive linear correlation between the time since 2002 and the number of deaths. Okay, so all that R value is telling us is how strongly correlated those variables are. Okay, a common phrase that you'll hear when discussing correlation is that correlation does not imply causation. Okay, so just because you can find a correlation between variables, it doesn't mean that one causes the other. Okay, so that causation is very important to understand, because people think that when you show a relationship between two variables or they're correlated, they think that means that one causes something else to happen. And that is not the case. Okay, so correlation does not imply causation. Just because the year goes up or time goes on, it doesn't mean that that is causing more drug overdoses. Okay, more drug overdoses as time goes on could be because of many different factors. The year is not causing drug overdoses. Okay, maybe drugs are easier to find, maybe they're more socially acceptable. Okay, there's all kinds of reasons of why the number of overdose deaths may be increasing. Okay, so you should always think about lurking variables when examining the correlation between two variables. A lurking variable is not among the explanatory or response variables, yet may influence the relationship among those variables. It does not have to be quantitative either. Okay, a lurking variable can be any kind of variable that affects the response variable. Okay, so for example, kind of a more upfront example, students who play golf may have a strong correlation with SAT scores. However, the student's family background will also be influential. Students who golf are much more likely to have better financial resources than those who don't play golf. So you may be able to plot an XY axis that has whether a student plays golf or not, or how much golf they play, and how high their SAT scores are. And there may be a very positive relationship that if they play golf, they have a higher SAT score. Okay, but it doesn't mean that just because they're playing golf that that's causing the SAT score to be higher. Okay, but if a student plays golf, golf is a fairly expensive sport, which means they probably have better financial resources. Okay, so what is the possible lurking variable in our example? Well, we already mentioned that with drugs, there may be societal pressures to do drugs, or more societal pressures now than there were years ago. I know back in my day, there's a lot more connectivity between people these days, which may allow them to, find drugs easier. So there's a lot of different lurking variables in why the number of overdoses may increase as time goes on.